Okay, Matt, this is where we got from the last slide. We have the KVL and the KCL. What shall we do now?
Well, I don't know, Sam, but somehow we have to get waves out of this. So
Yeah.
what do you suggest?
Well, okay, we have two equations. Let's see if we can find any relationship between the two equations.
Let's get a voltage equation first.
Yeah, let's start with voltage.
Okay.
So if we want voltage, let's see if we can take a second order derivative and get anything out of this. So
you're going to differentiate KVL with respect to Z, right?
Yes,
Okay, let's
exactly.
do that.
Yeah. So that would be second order derivative of this is equal to negative L di dt and dz.
Okay, so what you did was when you did the d by dz, you already flipped it around, right?
Oh, yeah.
But that's okay. Let's just leave it like that. Now what are we going to do? We want to eliminate I, so we need
Yeah,
the second
so
equation.
We can actually take the dt of this one
Yeah,
and
exact-
substitute in.
Right, let's do it.
Okay, let's do it. So di of dz dt.
You're going to
Yes.
take, you're going to
Oh, or
do
the-
you're going to do dt first, right?
Yeah.
We thought we'd do dt first. Then we can eliminate right away.
Yeah, thank you.
Okay.
dt dz is equal to negative c d squared v dt squared.
Wow.
Oh, well, what a pattern. We can just
Yeah,
substitute, make this substitution.
right. Let's see what the voltage equation
Okay.
looks like.
So I'll just write it here.
Yeah, right there.
dz squared is the negative cancel. You have L, C, d squared V, dt squared. Does this look right to you?
Yeah, perfect. Now, how do we get waves out of this?
This looks oddly familiar to some of the previous equations we've seen, right?
Right, but we need to find out about LC. So what are the
True.
units of LC? Because if we have the units right, this completely connects with the previous videos describing the wave equation. So let's see if we actually can get a wave speed out of this. What are the units of LC?
So L is Henry per meter, C is farads per meter.
So Henry farads per meter squared.
Yes.
Well, Henry Farad's pretty useless unit. I don't know what it is, but
Me neither.
I do know something about this. That when we take the second derivative, we're dividing by distance and distance again, distance squared.
Yeah.
So we're taking this and dividing by time
squared.
So this better have units so that the units all match. So what I
so
mean
you
by
need to cancel out the time squared and introduce the distance
Yeah,
squared.
so let's write this in terms of units. Volts over meters squared equals units of LC times volts over time squared. That means the units of this has to be such that we end up here with volts over meters squared in terms of units. So the units of this have to be something
time squared
like
over meter squared. So second square over meter squared.
So something like meters squared over time squared times voltage over time squared, and you see the time squareds cancel and the units balance, so the units of LC are meters squared per time squared.
That's
and
right.
what is meters squared per time squared? What physical quantity has those units?
That's velocity to the power of 2.
Yeah, velocity squared. So that means that this thing here can be rewritten as 1 over v squared. And so our final equation is the wave equation. If we replace LC by 1 over v squared, this whole thing can be rewritten. So let's do the rewriting of this equation. I'll put it up here. We get our final equation as something like d squared v dz squared equals 1 over the velocity squared times d squared v dt squared. And there's a similar equation for I, but we'll leave that for exercises.
Sounds good.
Now, what do? We've got the units. What's the application?
Didn't we show them a pretty map on your head?
Yeah,
Last time?
that map. Oh, there it is. There's the
Your head has been replaced by a map again.
Yeah, my head's gone. Well, I'll just keep working away here.
So last time you said the line is 14,000 kilometers long.
Yeah, so let's write that down. 14,000 kilometers. And the time for charging up the line will be 14,000 divided by the speed, 1/7 times 10, and that's going to be 14,000 kilometers, times 10 to the 8th meters per second. And doing the algebra, which is straightforward, we end up with about
1 second.
1 second. The wave will travel from one side to the other 14,000 kilometers in about 1 second, and that's a slow wave for the transmission line. So finally, after all this hard work, getting the equations here and the wave equation here, we have been able to calculate the charging time on the line, and everything is starting to make sense.
That's very exciting. I wonder what comes next.
What comes next is, well, we've been dealing with lossless lines, and we want to go further with lossless lines and see what the properties are of the voltage and current waves. So we'll look at that first, and then we'll put loss in the line. So that's
wow.
where we're headed in the next few videos.
Sounds great.
Okay.